Hello students. So the continued part of electromagnetic inductance that we are discussing today. So in the last class we talked about electromagnetic inductance and Faraday's law and Lenz's law. Okay. So today it's a continuation part. So we are today talking about self-inductance and mutual inductance. Okay, so for this, so first we'll go with the self-inductance. So for that, what I have to do, just consider a current carrying coil. Okay, just consider a current carrying coil. So somewhere here a tap key is also connected. You think like that. Okay, so in this current carrying coil, the magnetic flux is also there. In this current is flowing and this is the battery and this is the plug key. Okay, so here current is flowing through the coil means the magnetic field or the magnetic flux linked with this also changes. So if the current through this coil is changing, then the flux linked with the coil is also changing, and by this an EMF is induced by the magnetic flux. So this is nothing but the Faraday's law says. What Faraday's law says, when the current is flowing in the circuit, magnetic flux is changing and the changing magnetic flux will induce an EMF in this circuit. Okay, so this EMF we call it as the induced EMF, and Lenz's law says that the direction of this induced EMF is opposite to the change in the current. Current is changing, hence the magnetic flux is changing and hence the EMF is producing. So the direction of EMF and the change in current are opposite to each other. This is told by the Lenz law. So current is changing in this circuit in the sense current is either increasing or it is decreasing. Okay, so when in this circuit current is increasing, when in this circuit current is increasing, at that time how I and induced EMF are related to each other, and when the current in this circuit is decreasing, then how I and EMF are related to each other, that we have to study now. So here in this first case you just consider current is increasing. So when the current is increasing, the direction of I and the direction of induced EMF are opposite to each other. In the second case, when the current in the circuit is decreasing, at that time what happens? The direction of induced EMF and the direction of current are same. They are in same direction. This phenomena is called as self-induction. This phenomena is called as what? Self-induction. And the EMF in this phenomena, the EMF induced in this phenomena is called as what? Back EMF. EMF induced is called as back EMF. Okay, so now this is what? The phenomena of self-induction. So now you just consider any one circuit of this kind, you just consider. Okay, any one circuit. Okay, this is the battery and this is the, somewhere here a tap key is also there. Okay, so when the current in this whole circuit, when the current is switched on, first case is when the current is switched on, at that time what happens? So when the current is switched on means what? The current starts increasing in this circuit, right? So when the current is, when the circuit coil or the coil, when the coil is switched on, the self induction will oppose the growth of the current. Self induction will oppose growth of the current, because when the coil is switched on, current starts increasing, but this self induction will oppose growth of the current. Hence the current increases very slowly and it takes some time to reach from 0 to maximum value. So in this period of time, what happens? Energy is absorbed. Energy is absorbed. Similarly, second case, when the current is switched off or when the coil is switched off. So at that time what happens? Current starts decreasing or it starts to stop. Okay, means decaying of the current taking place. So when the current is switched off, the self induction will oppose the decaying of the current. Means in the both the cases it is opposing. When the current is switched on, self induction will oppose the growth of the current, and when the current is switched off, self induction will oppose the decaying of the current. Understood? So here also decaying of the current means switched off. This circuit is switched off means current is continuously gradually decreasing. So that decreasing, that decaying is opposite by the self induction. So at that time what happens? The current uh, to come to the zero or to stop, it also takes some time. So when the current is switched off, at that time energy is not absorbed, energy is stored or energy is released. I can say energy is released in the form of spark. Okay, so the effect of self-induction. How the effect of self-induction is there in this circuit, you observe. So the effect of self-induction is just similar to inertia. It's inertia and motion. So you know about inertia and motion. Na? Inertia and motion means what? It just opposes the body to change its position of state or rest or motion. Right? So that is inertia. So this self-induction, what it will do, when the current is switched off, it opposes the growth of the current. When the current is switched off, it opposes the decay of the current. Means it is opposing. Like so, it is called as what? Self-induction acts as a inertia to the circuit. Understood? So what self-induction exactly means is the the phenomena of the production of an EMF. The phenomena of the production of an EMF in a circuit itself due to the change in the current. Understood? Why? Because in this, see, self-induction is not anything gave back from any external things. It is self-developed. Understood? So this, hence the name itself indicate self-induction. So how can we define it? Means it is just the phenomenon of an induced EMF. EMF is induced. In this also EMF is induced back EMF. Here also EMF induced back EMF. So here also current is changing means the EMF is producing. But that is not because of the change in magnetic flux. That is self-developed. That's why we call it as the self-induction. Understood? So this self-induction is nothing but a phenomena of induced EMF due to the current itself. The phenomenon of production of an induced EMF due to the current itself is called as self-induction, and the induced EMF here is called as back EMF. Understood? So again, through the formulae, how can we define self-induction? Means, see, you know from the Faraday's law, you know it that pi is directly proportional to I. As the change in magnetic flux increases, the current also increases. So here pi is equal to one constant L and I. So this constant L, it is called as what? The coefficient of self-induction or the coefficient of self-inductance of the coil. So what is this coefficient of self-inductance? If I is equal to 1 ampere, if 1 ampere of current is flowing through the circuit, then pi is equal to L. Therefore, the self-inductance of a coil is the total magnetic flux induced. when a unit current passes through it. Understood? What is coefficient of self-inductance? The self-inductance of a coil is the total magnetic flux induced when a unit current passes through it. Understood? So this is what self-inductance or the coefficient of self-inductance. So the SI unit of self-inductance is Henry. SI unit of self-inductance is Henry. Okay, now you understood about what is self-inductance and how it behaves with an electric circuit, and how can we define it, and what is its unit. Okay, so now consider an example of one solenoid, one air tighted or closed solenoid, I can say. So just consider a solenoid. Just consider a solenoid, air closed solenoid. Okay, air closed solenoid of length L. Air closed solenoid of length L, of area of cross section A, and the wire is totally binded of n number of turns. Okay, and current of volume I is flowing through it. Okay, so this is a long air closed solenoid of length L, and total number of turns are n, and the area of cross section is A. So the total number of turns per unit length is nothing but n divided by L. You know that number of turns per unit length is n divided by L. So if the current I is flowing through it, then you know from already taught topics. You have done 3 derivations, na? Like magnetic field for a current carrying coil, magnetic field for a solenoid, magnetic field for a circular coil, like that. So there we derived that B is equal to mu naught mu naught I n divided by L, something like that only. This only, mu naught I n divided by L, this we have derived. So with this is for magnetic field at a point on the axis of a solenoid. So for this case the formula becomes what? B is equal to mu naught, as it is, n by L is there. So the total length is small l, n by L, and the current flowing in this solenoid is I. So this is the magnetic field of this solenoid. So flux, what is the magnetic flux through each turn? That is nothing but what? Magnetic field into area of the cross section. Hence mu naught n by L into I into A. Okay, so this is for what? Each turn. This is for every turn. Magnetic flux for every turn they have done. So the magnetic flux for total, let's consider this as pi A. So the magnetic flux for total n number of turns is nothing but n into pi A, right? So what is your pi A value? Mu naught n by L I into A. So pi becomes what? Mu naught n square I A divided by L. Okay. So now what we have to find now? You have to find the self-induction. What self-induction is equal to? Pi is equal to L into I. So L is equal to pi by I. So you already have the value of pi. So L is equal to pi by I. So mu naught n square I by A L into I, 1 by I. Okay, so what is the value of whole L remained for you is mu naught n square A divided by L. Mu naught n square A divided by L. So this is what the value for self-induction of a air closed solenoid. Understood? So this is all about what? Self-induction. So one more thing I told you is mutual inductance. So it is about mutual inductance. So before that, we can do some correction, means modifications here. What is it means? See here. I have written. See here. L is equal to mu naught n square A divided by L. So if we know this mu naught is just permittivity, absolute permittivity. Okay. Sorry, it is permeability. So you know mu is equal to mu naught into mu r. So in general, if this core of the solenoid, which is consisting a number of media, means so many mediums are there, means relative permeability also matters here. So mu r, it is relative permeability. So if this core is having so many media, then mu r1 is the relative permeability of the first medium. Mu R2 is the permeability of the second medium. Mu R3 is the permeability of the third medium. Similarly, with respect to the mediums, areas also will go on changing as A1, A2, A3. So, this formula, we can write it as L is equal to mu naught n square L. Mu naught is nothing but what? Mu is equal to mu naught into mu r. So mu naught n square L, and for different mediums mu r1 a1 plus mu r2 a2 plus and so on. Like this also we can write, because this is only in the case when only mu naught we are considering, right? Mu naught means the permeability. So in the different mediums, in the presence of different mediums, mu r also matters. Hence this is the generalized formula for self-induction of a solenoid. This you can use in solving the problems. That's why I'm telling this. Okay. Similarly, now we'll talk about the mutual inductance. Okay. And to this this self-inductance, you can also find it by using different experimental methods, like Rayleigh's method is there, Anderson's bridge method is there. Okay, so that is not necessary for you right now. That's why I'm not dealing with it. So now let's talk about mutual inductance. Let's talk about what? Mutual inductance. Self-inductance we discussed. So now what is mutual inductance? So what is mutual inductance means? So here I am considering two coils. I am considering here two coils. Two coils of this kind. Okay. So consider two coils which are kept close to each other. Okay. So when the current is flowing in this coil, and it is changing, when the current flowing in this coil is changing, the magnetic flux linked with the neighboring coil also changes. Understood? Because when the current is changing, magnetic flux also changes. So when the current is changing in this coil, magnetic flux linked with this coil also changes. So hence the magnetic flux is changing. Here the EMF is produced. Understood? EMF is produced. Okay, because current is not changing here, current is changing here, but the magnetic flux is changing here, and hence the production of EMF, induced EMF, takes place. Understood? This phenomena is called as mutual induction, and the circuit in which the current changes is called as the primary circuit, and the neighboring circuit in which the EMF is induced is called as the secondary circuit. So any two circuits in which there is a mutual induction, they are called as mutually coupled circuits. any two circuits in which there is mutual induction. They are called as mutually coupled circuits. So let I be the current in the primary coil, and then the magnetic flux pi also changes through the secondary coil, and that depends on I. Hence I can write pi is directly proportional to I, and pi is equal to m into I. This m is called as a coefficient of mutual induction, or simply mutual inductance of any two coils. And obviously if I is equal to 1 ampere, then the mutual inductance equal to magnetic flux. So what can we say? The mutual inductance of two circuits is numerically equal to the magnetic flux linked with the circuit when the current flows through the circuit is 1, or unit current is flowing through the circuit. And the EMF induced in S is nothing but what? Minus d pi by dt, and hence it is the mutual induction. We have to write pi is equal to what? M into I. So minus M into di by dt. The inductance produced here is this. Okay. So this also is measured in terms of Henry. And now again we will calculate the mutual inductance for solenoid. So how solenoid will be here? Because here we are considering two coils, right? In the self-inductance we only considered one coil. So here in the solenoid, in the mutual inductance case, we have to consider coaxial solenoids. Can you understand what is meant by coaxial? Lying on the same axis. Okay, so here we have to find the mutual inductance between two coaxial solenoids. Understood? So now consider a solenoid. How to draw this means, okay, so consider a solenoid of this kind. Okay, something like this. Okay, so here this is primary cells are this primary cell, and the secondary cell means somewhere like this, because they are kept like this, means this is primary and this is secondary, like this is primary cell we kept and this is secondary, and watching like this. Understood? So this is secondary cells. Yes, two coaxial solenoids na. So here let N1 be the number of turns in primary cell. Let N2 be the number of turns in secondary cell. And area means both of them are coaxial, means the area we can consider the single one. A is the area of cross section, and L is the length of the primary cell, and I is the current in the primary cell. So now what is the magnetic field at any point inside this primary cell? That is obviously mu naught N1 and I divided by L. And hence what is the magnetic flux through the each turn of the circuit is pi A, B into A. You just relate these things from the previous ones, B into A. So mu naught N1 IA divided by L. Now since the secondary is also wounded closely over the central portion of the primary, means this is the primary cell, means this is secondary cell, like this. So the central position of primary is closely wounded to the secondary cell na? So we can say that the same flux is linked with both of them. Understood? So the magnetic flux through each turn of the secondary cell can also be mu naught N1 IA divided by L. No? Sorry, it is N2 turns. So the total magnetic flux, So the total magnetic flux through the coils is mu naught N1 N2 Ia divided by L. And what is mutual inductance? M is equal to what? Pi is equal to M into I. M is equal to pi by I. M is equal to pi by I. So what is your pi? Mu naught N1 N2 I get cancels L. Okay. So this is what the formula for mutual inductance. Now again here we are having mu naught. So if the core is a material of permeability mu r, then M is equal to mu naught mu r N1 N2 A divided by L. So again here we are having if so many number of mediums, mu r1, mu r2 and so on, a1, a2 and so on. So what is the value for total M will be? That is mu naught N1 N2 A by L, N1 N2 by L and mu R1 A1 plus mu R2 A2 plus mu R3 A3 and so on. Understood? So this is the formula for mutual inductance, right? So on this concept you have to solve some problems, and I'm thinking to solve all the problems after completion of the chapter. So you just keep on recording the things on your own, and that's all. Okay, so this here I'll end the today's class. If you having any doubts, ask me. Okay, thank you.